Welcome to this pre-class video on aldehydes and ketones. Well, one of the more important things that we do in this class is being able to look at an organic compound and classify it, because that helps us predict some properties of a molecule. So, two important families or classifications of organic compounds are aldehydes and ketones. Aldehydes have a general formula, R, and we know R is a rest of the molecule. It's typically in our class just a hydrocarbon group. R, C double bond O, and remember C double bond O is a carbonyl group. R, C double bond O, H. Ketones are similar, but this difference really makes them have different properties. It's R, C double bond O, the carbonyl R. So there is no C double bond O H. So there's no hydrogen bonding to a carbon that's part of a carbonyl. Again, this gives aldehydes and ketones different properties. Now, aldehydes, when you come to naming them or recognizing the name of an aldehyde, they're going to end in AL. Al for aldehyde. And then ketones end in ONE for ketone. And so when we start naming them, or if you are given a name, you can determine what type of classification you have, typically by how the name ends. Okay? Well, let's do a naming example here. I've given you the molecule below, and it is clearly an aldehyde. If we start with this molecule here, it is clearly an aldehyde, but I've drawn it in this kind of ultra condensed form, and it may be to your advantage to redraw this before you start trying to name it. So really, this molecule, when I give you this ultra condensed formula, I'm really telling you this is the formula, or the structural arrangement. So don't ever be afraid to try to redraw the molecules to help you better understand how the atoms are connected. There we go. We clearly have an aldehyde. When it comes to naming aldehydes, we want to find the longest continuous chain of carbons, but it has to contain the carbonyl group. And in fact, ladies and gentlemen, with aldehydes, the carbon of the carbonyl is always number 1. Because it's at the end. This is at the end of the chain. So when we name aldehydes and start numbering the longest continuous chain, hey, make that your number 1 carbon, the carbon of the carbonyl. And then just go from there. 1, 2, 3, and then everything not in the parent is in a substituent. So this is chloro, and this is chloro, our old friend chloro. There's 2 of them. So when it comes to naming, we're going to have 2, 2 dichloro. I'm going to put a dash here because I'm just changing lines, okay? And now there's 3 carbons, so that's prop and al. Prop and al, because we have an aldehyde, okay? Alright, so 2,2-dichloropropane-al. If you look at the molecule down below, I think we clearly have a ketone. We have an R, C double bond O, R. And so with ketones, okay, except when we have a cyclic ketone, a ketone that's part of a cyclic structure, the carbonyl carbon will never be number 1 unless it's cyclic. This is not cyclic, so we have to pick an N to number from. But what we want to do is we want to make that carbon, now the carbonyl, the lowest number possible. That's the rules we've been dealing with, right? So 1, 2, 3, 4. Now I'm at a branch point. I've got a decision to make. We're at a crossroads in your life. Are you going to go straight across, or are you going to kind of go down to pick up the carbons? Well, if you go down this way, you can pick up 4 or 5 carbons. If you go across, you can get 4. If you go down, it's 4, 5, 6. If you go across, it's 4, 5, 6, 7. So the choice is clear. Well, that means this has to be a substituent. And guess what? This is one you need to know. This is iso propyl. 3 carbons, so it's propyl, and the connection point is at the center carbon, not an end carbon, so it's isopropyl. Well, hey, we're ready to name this thing. It's going to be 4-isopropyl. Now with ketones, if it's not cyclic, you need to put a number to tell where the carbonyl group is at. Because in the ketone, that carbonyl group can migrate around. Alright, and the name must uniquely identify the molecule. So we have to have a number to tell where this carbonyl is at. So it's 2. There's 7 carbons, so that's hep 10, and then it's ketone, so it's ONE. So again, just a couple of quick examples for naming. Well, you've probably picked up on this, but we do a lot of things in this class about properties of molecules. That's very important. And so you will, when I give you a problem along these lines, you will never be able to, quote, memorize the answer because you don't have any clue what molecule I'm going to give you. But you can analyze, given a set of rules that I've given you, which has a higher or lower water solubility or higher or lower boiling point. Again, this is all about analyze, not memorize. Okay? So what do we got? We got 2 molecules. This molecule is, I hope you will agree with me, a primary amine. And this is, hey, this is a ketone. So I've got some questions for you. I need to know which has a higher or lower water solubility and a higher or lower boiling point. Well, luckily we've got some guiding principles that we've gone over on how to analyze this situation. So when we look at the molecule A, in terms of water solubility, you know that water solubility largely depends upon the ability of a given molecule to form hydrogen bonds with water. Therefore, we want to do a quick D plus A calculation. D being donor, hydrogen bond donor, A being hydrogen bond acceptor, little a. Okay? So D plus A equals 2 plus 1 equals 3. Now you may say, where's this acceptor at? I don't see a lone pair in the molecule A. Well, you have to know that there's a lone pair there. You have to know there's a lone pair there. Alright, well, let's analyze B. D plus A is, there's 2 donors. Oh look, I've already drawn in the lone pairs on this ketone. So we know we have acceptors, 2 of them, but we don't have any donors. There's no hydrogen attached to X, where X is FONORS. So donors is 0, there are 2 acceptors, so D plus A equals 2. So clearly A has the advantage in terms of water solubility. It has a greater capacity to form hydrogen bonds with water. Now, what about the nonpolar area? Well, it looks like in this case we've got molecule A has 3 carbons, molecule B has 3 carbons, and in terms of nonpolar area they're going to be similar. I would say that probably the R group of A might be a little bit more nonpolar than the combined R groups of B, but if it's close like it is here, the hydrogen bond donors and acceptors will basically be the deciding factor. So based on this information, then A has a higher or greater water solubility. And again, because it has a greater capacity to form hydrogen bonds, the nonpolar area is not that different, so we're going to go with A. In terms of boiling point, really boiling point of a molecule is a measure of what we would call self-association. How well do the molecules associate or cling to each other? Well, the first question to ask along these lines is, can a molecule H bond with itself? Now, if a molecule can hydrogen bond with itself, that is, if you give two of those molecules, they can form a hydrogen bond, then that means that a bunch of molecules just like that, can also form hydrogen bonds with each other. It tends to raise the boiling point. So let's answer this question for molecule A and B. Well, can A hydrogen bond with itself? Oh yes, there's a donor in the molecule and an acceptor. So if you had two molecules of A, you could draw them, yeah, you could draw them forming a hydrogen bond. Molecule B, on the other hand, there's no donors at all in molecule B. So can two molecules of B form a hydrogen bond? Absolutely not. No. No. Now, the other factor is size. How big is the molecule? Again, the rule is the larger the molecule tends to be the higher the boiling point. Well, both of these molecules, A and B, they both have what we call the same number of heavy atoms. That is, how many non-hydrogen atoms? In molecule A, there's 1, 2, 3, 4 non-hydrogen atoms. In molecule B, 1, 2, 3, 4. So both have 4 what we call heavy atoms. That's just a quick and dirty way to tell if they're the same size or similar in size, and they are. So basically, these results are telling us something very clear. They're both about the same size, and one can hydrogen bond with itself, the other one can't. Ladies and gentlemen, A has a higher boiling point. And again, when we do these types of answer these types of questions, it's about comparisons. A versus B versus C versus D, perhaps. Well, the last part of this pre-class video is really, it deals with reduction of aldehydes and ketones. We already know about oxidation and reduction, and we've talked about the oxidation of alcohols. This is a previous topic now. The oxidation of alcohols can give an aldehyde or sometimes a ketone. Well, what we know with aldehydes and ketones, if you start with them, you can reduce them back. You can reduce them back to an alcohol. Okay, so for example, let me give you an kind of a overview. If you have a carbonyl group, which you do in both an aldehyde and a ketone, if you treat them with a reducing agent, there are 3 reducing agents that you need to know. And you can kind of identify reducing agents because they have a lot of hydrogen in them. Look at that. H2 with platinum is one. What's called lithium aluminum hydride, or LiAlH4, is one. Or sodium borohydride, or NaBH4. Those are reducing agents. Really, we're not going to get into the mechanism of this too much. But what we know is you basically, when you reduce a carbonyl containing molecule like an aldehyde or ketone, a hydrogen is added to this oxygen, a hydrogen is added to the carbon of the carbonyl, and one of the double bonds goes bye-bye. So what you end up with is the following. So there's one hydrogen there, there's the hydrogen there. And so basically, if you start with an aldehyde, the molecule you start with, if the carbonyl you start with is in an aldehyde, let me write that a little bit better, or a ketone, and you reduce it. So you add a reducing agent. And you may say, well, what's a reducing agent? Well, one of the 3 that's listed here. If it undergoes reduction, you end up with an alcohol. You end up with an alcohol. Again, this is a very useful chemical transformation. Well, let's do an example. Let's say we have 2-methylcyclobutanone. Oh wow, I've given you the name, and so to do this, you're going to have to draw the structure based on the name, but you know how to do that. It's cyclobutanone. So the first part of the molecule I'd pay attention to is cyclobute. So you know you have cyclobutane, but it's a ketone. and it's 2-methyl. Look at that. So when you number a cyclic ketone, this carbon here is always number 1. Okay? Again, if it's not cyclic, the carbonyl will never be number 1 in a ketone. But this is a cyclic ketone. We have a different set of rules. Well, can you draw the structure over here? Well, we have this plus lithium aluminum hydride. All you really need to remember is that one hydrogen goes to the oxygen of the carbonyl, another hydrogen goes to the carbon, and one of these double bonds goes bye-bye. And if we redraw it, we have this. So now we have a cyclic aldehyde where you have an OH group, a hydroxyl group coming off a cyclic system. So that would be the structure of the product that I would want you to draw. You can also, since we talked about alcohols, you can also name this. And so when you have a cyclic alcohol, this will be carbon number 1. And then you're going to number the chain, number around the cyclic system to get the lowest combination of numbers possible. So 2, 3, 4. So, ladies and gentlemen, this is 2-methyl cyclo bute and ol. You may say, well, I thought we had to put a number to tell where the OH group was. And I would say if it's not cyclic, you'd be correct. But this is a cyclic alcohol. You don't need the 1. So this is kind of an overview of aldehydes and ketones that we'll be talking about in class. Hope this video was useful.